Dear viewers, welcome to the UGC lecture series in biophysics. Now we are go through part 2 of the methods to determine the protein structures. In part 1, we have been looking into the problems like molecular replacement and single isomorphous replacement, and what are the drawbacks in MR and also your single isomorphous replacement. Namely, in MR we have to have a model which is at least having such a homology of 25% or more. In SIR we should have another derivative, and the second derivative should not substitute at the same place. So many complications were there. So now let us see how this could be overcome. The methods proposed by Professor David Harker from US. By choosing two isomorphous derivatives, let us say with heavy atoms H1 and H2, not substituting at the same positions, David Harker made a geometrical construction to overcome the twofold ambiguity. That also we have seen in the part 1 program, because we determined some angle alpha prime from the cosine function. So, that can be plus or minus. So, the total protein phase is nothing but heavy atom phase plus or minus this alpha prime plus pi by 2. So, totally we have two choices, and whichever angle is closer to the heavy atom phase, that is supposed to be the correct phase for the proteins. Now, let us see what David Harker made regarding this construction, which are known as Harker construction. So, this is also called Harker circles. If you look at the left hand side figure, how to overcome the twofold ambiguity you get because of the use of single derivative. So, here we are using two derivatives, and for clarity let us go to the next picture, and this is the ambiguity. When you take first derivative, mod f p can be this way or mod f p can be this way. So, when mod f h is added, so here we get mod f p h, here mod f p plus mod f p h, here we have mod f p h. No? So, now we have two circles, one circle drawn with center O and radius mod f p, another circle drawn with center O with radius mod f p h, but this can go this way or this way. So, twofold ambiguity is there. How to do it? This twofold ambiguity in the phases can be resolved if you have one more derivative. Let us see how the Harker circles go. The first is same with O as center, and just say these are all modulus only. So, do not confuse. With mod f p as radius, I draw a circle. This is the red one, red arrow I am showing. Now, what you do is, when you have the first derivative, then we have the contribution for the derivative going this way. So, is minus f h 1, and this plus this added you will get your f p h 1. So, with the shifted origin to O 1 prime and with the radius f p h 1 mod f p h 1, I draw a circle. So, this is this circle. Then for the second derivative, this is going this way, this O is shifted to O 2. Now, mod minus f h 2 added with the f p, we get your f p h 2. So, now with O 2 as the third circle origin and with mod f p h 2, I draw this circle, three circles. If you just see here, two circles intersect at different points, but there is one point, unique point, where all the three circles meet. Just clearly see, first circle, then second circle, third circle, all of them meet only at one point, this unique point. Therefore, this is the unique value alpha p. Okay. So, this is called geometrical construction by Harker circles. So, now these Harker circles are used to solve the phase ambiguity when two derivatives are used. Now, if we do a Fourier with a coefficient mod f p h 1, the difference in such a factors between the second derivative and first derivative, since you are using square, is a Patterson actually, then this was proposed by Rossmann. So, coefficient, this coefficient when you use as a in a Fourier, or if you do a Patterson with this difference in such a factor called difference Patterson, we have the final result coming this way. the last term in this equation, namely right hand side, is known as the correlation function of the product of two Fourier coefficient. Okay. So, Fourier coefficient 1 is there, Fourier coefficient 2 is there, then this is a cross term. So, this is about the MIR. So, these confirmations what you call difficulties were existing up to 1980. So, now nobody is going to MIR, because if you look into the molecular biology experiment, it is easy to have your derivative station is a technique, that is the right terminology. We have two amino acids with sulfur, one is cysteine, other is methionine. When you do the protein expression, it is possible to change methionine as selenomethionine, that is known as derivative station. Sulfur is replaced as selenium, it is a heavy atom. Here every atom has its absorption edge, and selenium has an absorption edge close to 0.94 angstrom. So, it behaves like an anomalous scatterer. So, native stage itself in a protein, when it is expressed, automatically suppose you have 2 methionines, 2 selenomethionines will be there. So, 2 seleniums will be there. If it is 4 amino acids are methionine, 4 selenium derivatives will be there. So, there is no question of preparing multiple derivatives and so on, complications are completely avoided. So, now in all the synchronous radiation throughout the globe, one beam line is already tuned to the selenium absorption frequency. So, data can be collected at the tuned wavelength, where due to the anomalous scattering effect, substantial number of Bragg reflections which differ in intensities of HKL and intensity of H bar, K bar, L bar reflections are called the inverse reflection, could be measured very accurately. So, here you can ask me why there are two techniques, multiple isomer of anomalous diffraction and SAR. Initially, the detector technology was not that great. So, to overcome the ambiguity, people used to collect data at 3 wavelengths, which I will show you from the graph. But later on, the detector technology has improved a lot. The intensity difference between this, even if it is less than 0.5%, you can measure accurately. That is why people are jumping to single wavelength anomalous diffraction SAR. Okay. Now, already we have seen there is a Patterson map called anomalous difference Patterson. What do you mean anomalous difference Patterson? Since intensity of HKL reflection will not be equal to intensity of H bar, K bar, L bar reflection, if we take square root of this, we get modulus f of HKL. This is square root modulus f of H bar, K bar, L bar. So, by virtue of this not being equal to this, we have mod f of HKL will not be equal to mod f of H bar, K bar, L bar. So, now if you do a Patterson with this difference due to anomalous scattering, that is known as anomalous difference Patterson. So, this difference is caused because of this heavy atom. Therefore, this anomalous difference Patterson will get you the position of the heavy atom, which can be used to get the phases. Then we can straight away do the electron density calculation, assuming your initial phase is the heavy atom phase. So, this is what I am telling here again. Earlier to the development of sensitive detectors, macromolecular crystallographers used to collect synchrotron data at 3 wavelengths. Okay. Now, already we have seen in our presentation or lecture series in anomalous scattering. So, let us see what is anomalous scattering. Every object has a natural frequency of vibration. When the external frequency of vibration matches with the absorption edge of an atom, some strange effect happens. This happens in sound. There is a sonometer experiment, and this phenomenon is known as resonance. In X-ray crystallography, if the incident wavelength of X-rays or the incident frequency of X-rays matches with the absorption frequency of a heavy atom in the protein, then the atomic scattering factor F, which is normally F naught real part, started to have two corrections, one in the real part which is a negative value, and another in the imaginary part which is a positive value. So, this modulus of this anomalous scattering structure factor is nothing but squares of this real part added with squares of F double prime, then take square root. Okay. This is the thing. So, this is the atomic scattering factor in the presence of anomalous scattering. So, here it is normal thing. Remember that f prime is always is negative, f double prime is always positive. Now, you do data collection at 3 wavelengths. First, at a wavelength lambda 1 closer to the absorption frequency called the peak wavelength, where these intensities between h k and h bar, k bar, L bar will differ. At this wavelength closer to the peak wavelength, we have the maximum value for f double prime. Then you measure the data at another wavelength lambda 2, this is known as inflection point, where f prime, the real part correction, has the maximum negative value. So, if you look at the graph, one f double prime curve will be going upper side, f prime curve will be going downward. Okay. Then 2 more wavelengths we can collect data lambda 3, lambda 4, the left and right remote. Okay. Now, any change in f prime, okay, by tuning the wavelength to the 4th decimal, I can make f prime to change even by 2 or 3 or 4 electrons, which means that when it is added here minus 3, minus 4, minus something, instead of f naught some heavy atom, it behaves like another atom with atomic scattering factor f naught minus 2 electrons, f naught minus 4 electrons, f naught minus 6 electrons, and so on, which means that you are physically changing one species to another species. Even though selenium is there, you are making selenium to behave like another atom with lesser number of electrons. 3 such atoms can be made physically, not chemically. Okay. So, that is what I am mentioning here. Any change in f prime negative will alter the total real part of the anomalous scattering factor term, and this is equivalent to the substitution of one heavy atom in place of another. Because when you, let us say, suppose you use platinum, it has one atomic number. So, that is our atomic scattering factor, roughly number of electrons. Instead of platinum we use gadolinium, that has different value of electrons. Okay. So, same way I am not using different species, but by changing this I am changing the atomic number. So, that is the thing. So, look carefully this graph. So, this is when X-ray energy, incident energy is changing to different values. Okay. Now, this is the atomic scattering factors. So, look here, this is 0, above that we have positive value, below that we have negative. If you look at the variation of f double prime curve, it is completely in the positive region. Okay. F double prime becomes more or less flat, suddenly at one point goes up. This is known as peak. At this point called peak wavelength, we can have thousands of Bragg intensities, where the intensities of h k reflection will not be equal to h bar, k bar, L bar reflection. So, this is called Biefeld difference. By feeding these pairs as coefficient in Patterson, I can get the position of heavy atom. Now, look here, near to the same place here, if we just drop a line, we have f prime becoming most negative. So, what I mean is my statement is that, let us say I change the energy, let us say 10,000. At 10,000, if you drop a line, it hits here. So, roughly it is minus 1.8. Then I collected 12,000, comes here, it is minus 4. So, this f prime is added in the real part f naught, which is equivalent to by changing one atom to another atom. So, that is called your tuning, this is called tuning. So, this happens even if the 4th decimal change in wavelength is happening. So, now this is known as peak point, this is known as inflection point. You can collect data at either this energy or this wavelength or at this wavelength. One is called left remote, another is known as right remote. Usually, when the detector technology was not that great, people used to collect at 3 wavelengths. One is peak, one is inflection. Peak is a point where f double prime is the largest value, positive, and inflection is there where f prime has the least value, most negative, and you can choose one point to the left hand side or the right hand side. These are called left remote or right remote. Clear? So, together is known as MAD technique, and this alone is known as SAD technique, single wavelength anomalous diffraction. This saves you time. So, we have 2/3 of the time is saved, because we are collecting only one data set. For the same Bragg reflection H, the intensity collected at inflection point and at the left or right remote will differ. This difference due to the change in intensities or structure factor magnitude. At when you collect one wavelength, I will show you the table also, whatever data we have collected, this synchrotron will show you, that will make you clear. So, this is one wavelength I collected, okay. Then remote wavelength I collected, right. If you look at the HKL and H bar, K bar, L bar, the difference will be very marginal. Therefore, I merged the data HKL and H bar, K bar, L bar, I added divided by 2, that is one amplitude at one wavelength. Same reflection, when you go to the another wavelength, where we have the equivalent of physical substitution by changing of f prime, we have different value for this. So, since this value same reflection, this is also same reflection, but values differ, I can use this as the coefficient, do a Patterson, and this is known as dispersive difference Patterson. First we have seen anomalous difference Patterson. In anomalous difference Patterson, we use same wavelength HKL, H bar, K bar, L bar differences, that you do a Patterson. In dispersive differences, same reflection, but different wavelengths. Clear? Do not confuse. Okay. Now, the Patterson with the square of this as the coefficient is known as the dispersive difference Patterson. So, we have two different Pattersons. One is bifid difference Patterson with a single data collected at the peak wavelength. Now, f of h and f of h bar at peak wavelength. Second is dispersive difference, where we collect use of the data for same reflection at two wavelengths. Now, so this is if you want to reconfirm your position of heavy atom, you can even use it. Now, you can use MAD also, SAD also, no problem. We can now technology, as I told you, even 0.75% difference between HK and H bar, K bar, L bar can be accurately determined. Now, this is important. So, at peak wavelength lambda 1 I have given here, selenium atom has an absorption edge, or at the wavelength 0.9788 it has a maximum value for f double prime. Because of this anomalous scattering, intensity of your HKL will not be equal to intensity of H bar, K bar, L bar. So, if you take square root, your modulus of FHK will not be equal to modulus of FH bar, K bar, L bar. Okay. Because they are unequal, you take a difference of this and do a Patterson. This is known as bifid difference Patterson or anomalous difference Patterson, which will get you the position of the heavy atom. You can use that position as a rough phase angle to do the further calculation. Let us look at the table. This table shows the data collected in a synchrotron at the Brookhaven National Laboratory for one of the crystals, for which I collaborated with Dr. Shekhar from Indian Science Bangalore. I went there to Brooklyn, the Brookhaven lab. So, this data I am just showing for some of the reflection at the peak wavelength. This same crystal I have tuned it to the edge wavelength, where f prime will be the least, no, I am showing same set of reflection. Then I am showing at a remote wavelength what will be the thing. Just look at when you collect at peak wavelength, in plus means HKL reflection, minus means H bar, K bar, L bar reflection. Okay. The 1110 Bragg reflection I plus, that is mod FHKL is 4297 roughly. Then same thing mod F H bar, K bar, L bar is 4478. See here, the difference between this thing is more than 100, right. Now, since it is more than 100, so these differences can be made use of in a Patterson. So, this is happening because of anomalous scattering or bifid differences. So, I call it as a your anomalous difference Patterson or bifid difference Patterson. Now, you look at 1110 at the edge where f prime is the least 3824. Now, it is 36. This is 2664, 2657. No, between 2664 2657 difference is only very marginal, 705, 692. So, in these cases you add this with this and divided by 2. So, even though your I plus and I minus differ at this wavelength also, the difference is not that much as in the peak. So, here you merge the data. Okay. When you merge it, roughly I am getting around 700, let us say 1120, I am getting roughly merging 700. Same 1120 go here. This is 570 plus reflection minus reflection 605. Again, if you average, we get maybe 580, right. Now, between these two wavelengths, remote and edge, I am just giving only one example for a particular reflection. 1120 at the edge or inflection has roughly 700, whereas here it has 600. So, difference is there 100, and this difference is due to the change in real part correction f prime, right. So, this is known as dispersive difference. So, between this data and this data, lambda I and lambda r, same reflection, I find the difference, I do a square of it, then do a synthesis which is known as a dispersive difference Patterson. I can get the position of the same selenium atom, whether this selenium position, this selenium position are matching, usually it will match. So, this is known as MAD technique, because we are using 3 wavelength, and SAT technique. So, in summary, what you have to learn is this important topic what we have seen today. Phase information is needed in diffraction to calculate a Fourier to locate the atomic site, but unfortunately the Fourier methods require not only the Bragg intensities from which you get such effect amplitudes, but also the phase angles of these Bragg reflections, but experiment does not directly gives you the phase angles. So, this bottleneck, namely the non availability of the phases to compute Fourier synthesis in order to locate atomic site, is known as the phase problem. So, in small molecules we have seen that direct methods or the mathematical methods using probability theory can be used to overcome the phase problem, and 99% of the small molecular crystal structures have been solved by this method called direct methods. We as of today we have more than 11.5 lakhs of small molecular structures determined by direct methods. Now, for the macromolecules, the probability methods fail because the number of atoms become large, the probability distributions have become sharp, it becomes more or less flat. So, here we used methods like molecular replacement, we have seen single isomorphic replacement and multiple isomorphic replacement. Each of these methods have their own limitations, we have seen, and in the case of anomalous scattering method, these limitations are not there, and of course, anomalous scattering method resembles MIR. MAD resembles MIR with 100% isomorphism. So, that is the reason why the number of protein structures determined as on today after 80s are exponentially increasing. We have more than 1,60,000 protein structures determined, and most of them are determined using SAT, and they are deposited in the data bank known as protein data bank. So, we have also seen that the process of searching unknown structure using homologous structure, which is termed as molecular replacement, for which at least 25% homology is required between these two structures, and we have also seen that heavy atom techniques can overcome the problems in MR, but they have their own limitation because the sites should not be the same when you use multiple derivatives. Then finally, MAD or SAT technique came to the rescue, and we have number of structures determined using the last technique known as MAD or SAT. So, these are the important references. Whatever we want to refer, you can see theory and practice of direct methods in crystallography. Particularly, if you want to look at the small molecule structure determination, experiment aspect, you can refer to the Duncan McCree book, Practical Protein Crystallography, and this is a very good book, voluminous book, Biomolecular Crystallography Principles, Practice and Applications to structural biology by Roop, and we have seminar conducted in 1997, aspects of crystallography molecular biology. This is edited volume by Professor Parthasarathy, my mentor, and Glusker. Of course, Fourier methods are well known, and Ramachandran and Srinivasan have edited a book, Wiley Publications, and we have in the field of MAD technique, Hendrickson, a very good paper is there. We have other papers for molecular replacement and translation function, rotation function like Blow-Crick method, Rossmann, of course, Harker's original paper, Harker, Parthasarathy, Katta Parthasarathy, because they have very good papers. Two parts are there where they talk about MIR and also MIR and anomalous dispersion. If you are interested, you can go through the papers. Now we have a sound background about MIR and anomalous scattering. I am sure that you will be able to follow these reference papers. Thank you.